All right, stream is up.
Perfect. So welcome everyone to the Adding Decentralized Off-Chain Compute to Your dApp workshop. Here we have Bernhard from Fluence, who's going to be leading it. So yeah, if you guys have any questions, feel free to drop them into the chat and he will get to them as soon as possible. But if you guys are not able to get your questions answered, or if you have any questions after the workshop, feel free to contact him and the Fluence team through the sponsor Fluence Discord channel. All right, Bernhard, all yours.
All right, thank you very much. All right, as it's been pointed out, my name is Bernhard. I'm part of the Fluence team, and thanks for being here, and thanks for having me, and thanks for being interested in the hackathon. It's going to be an awesome time. Today, I want to do a workshop-y kind of thing, program decentralized compute and IPFS with Aqua, and the next 10 slides are so basically all about unpacking that headline. So let's dive into it. Fluence, what is Fluence? Fluence is an open permissionless peer-to-peer protocol that's focused on compute. Aside from the protocol, we provide a network and a vast open source tooling repository that allows you to, in our opinion, really take on distributed, in particular, peer-to-peer programming at a level of ergonomics and convenience you probably haven't experienced before. And we'll get to that. The way things work, sort of roughly bird's eye view, is we use WebAssembly interface types as our highly portable compute modules. They execute on what's called the Marine runtime, which is a general purpose WebAssembly runtime built on Wasm, which we have on each network peer. And then you, from these modules, you create services. So WebAssembly modules themselves share nothing. And how we build services, which are logical constructs, we do them by linking those WebAssembly modules to a JSON file, which establishes the dependencies. And now you end up with very powerful service constructs that allow you to execute external effects, including download, upload, modify, and replicate, and interact with other networks or participants of other networks as well. And if you look at the right there, get to peer-to-peer network, the greenish things are sort of, I don't know, could be clients, could be browsers, any kind of client IoT. And then we get a couple of services here. And as you can see, you can write adapters essentially to interact with the outside of the Fluence peer-to-peer network, basically bring in your traditional Web 2 APIs, microservices, or actually Web 3 networks like IPFS. And this is where we're really going to focus sort of throughout the workshop. And now, if you look at this, so you got this peer-to-peer network, you got a bunch of peers, you got a client, and you got services that are hosted on nodes. So yes, there's a way to deploy those WebAssembly modules with the configuration onto these nodes. So now you're looking at it, it's like, so how do you actually program this? For most of you, not most of you, but for those of you who have experience with blockchains, which is probably the biggest peer-to-peer, I don't know, consumer these days, you interacted through JSON RPC or even REST endpoints. In Fluence, this is not the case. And the reason this is not the case is because it's a general purpose environment where pre-specifying JSON RPC endpoints is impossible because you as the developer create those services. So the question now is, how do you actually harness those services? How do you compose them into a application? And this is where a special purpose language Fluence created. It's totally open source. Everything's MIT or Apache 2 or both, to program distributed networks and services. Now, the interesting part is it doesn't just apply to the Fluence network. You can actually use Aqua to compute and compose services, not compute, just compose services that include networks, outside networks, and outside applications. And that's actually really powerful. And we'll see this, how you can use custom services in conjunction with IPFS through Aqua. which is I mean, it's a 10 line, you'll see it. It's going to be awesome. And we believe the ergonomics of Aqua is such that it really going to commoditize peer-to-peer programming in it by itself. So what does it look like? So it was a lot of talk, a lot of how wonderful it is. Let's put the pedal to the metal here, the rubber to the road. Go right to the bottom. This is a very simple example of a Hello World service. So the assumption here is we have a service already deployed on a node, and that service is a greeting service with the function greeting. So basically that greeting function, which we would have written in Rust and compiled to WASI 32, takes two parameters, a string and a Boolean. The string is the name, and the Boolean is basically whether or not we greet the caller. So a Boolean of true and a string of Joe or ETHOnline, for example, would be hi ETHOnline, and false on the Boolean would be a bye ETHOnline. So fancy hello world. So lines 1 through 2 basically show you how to create the interface within Aqua. This is literal Aqua code, and how we can map that to the deployed service through this WebAssembly modules through what's called the service ID. The service ID is unique as you create a service from those modules. You can literally create 10 services from the same modules if you want to on the same node, and you get 10 different service IDs, which has advantages if you want to do this. And then lines 4 through 8 are the actual Aqua function. This is the composition, if you will, of that greeting service. And that gives us a result at the end, basically, the hello or the hi or bye, whatever the name is. And in addition to the name and the Boolean, the name and the greet, the string and the Boolean we saw in the greeting service signature, we also have a node and greeting service ID parameter. The node is the peer ID of the node or the peer on which the service has been deployed. And the greeting service ID is the unique ID associated with that service, which is comprised of reusable WebAssembly modules. So what we're doing now is we're basically saying on this node, on this peer specified, follow my cursor here, we bind this interface, this Aqua interface, to the actual WebAssembly interface. We then use that binding and call the function greeting, which is part of that interface, with the provided parameters of greet and name, and then we return the result. And then that's it. This is, you just basically harnessed a distributed peer-to-peer service in basically 8 lines. And if we go back and look at it from a diagram perspective, so what you basically did is, let's just say you're in a browser. And for a browser, you need a relay. For those of us a little newer to peer-to-peer networks, a relay is a publicly accessible peer, because not all peers, because of NAT requirements, may be publicly accessible, but they might be accessible through a peer. Browsers are not directly accessible, so they have to go through a relay at all times. And so basically what we would have done is we would have called from this peer on the relay, and then on the relay we would have determined, okay, let's just say this is our service, our hello service. We call this service, we execute it there, and then we bring back the result, which could have gone to the client we initiated with or some other client. And if you look at it, this basically on the little sequence diagram there, so we initiate this greeting, we call it, we execute it on that node, and then we return the results via the relay back to the client peer. If you expand that model, you'll very quickly realize this leads to a very, very different request response model than you usually see. In your traditional client server environment, your response model is request response back to the client, request with that response back to the client, and on it goes. So if you wanted to do say a credit card authorization, and I don't know, let's just say you want to use Stripe for that, and then you want to send your customer a SMS of the outcome of that credit card authorization, you basically, in a typical client server environment, you call Stripe. Then you get the response back. Then you call your SMS service, which could be twilio, and you notify the customer, and that is it. So request response, request response. In a properly, or not properly, but in a commonly designed peer-to-peer application workflow, like we're looking at, you don't necessarily have that at all. What you can do is you basically can forward your response to the next service. So if we look here, and let's say we want to do this this very example I just said, and you have I don't know, out here you have Stripe and twilio. So the first service would call Stripe, get the response, then feed it directly into the next service, which I don't know, where micro somewhere over there is twilio, and then you get back your okay or whatever to your browser. You make this a large number of hops in a request response model, and all of a sudden what you realize is you have a very, very thin client. Everything happens on the network, and that's extremely powerful because it allows you to minimize the client requirements. And I mean, I'm sitting here with a pretty damn nice laptop and a pretty fancy phone, but the majority of the 8 billion people out there are not running this big network, this big laptops or desktops. They're Chrome OS type situations, and same on phones. So thin clients, and then if you add edge devices, various IoT devices are going to be a huge volume, and they'll extremely benefit from having this redistribution of the workload to the network. And that's one of the things we're super, super excited about. The other part, of course, is why do we do what we do? Well, first of all, if you look at it, if you look at that workflow, you stay in control of your data. And to us, this is a really, really huge Web3 benefit. And you also don't have any centralized brokers, which means you're not tying into various cloud environments necessarily. And also you get very, very censorship resistant. It's not censorship proof, but it's definitely censorship resistant. And there's a lot you can do in terms of deploying multiple services on multiple nodes in different geographies that really, really strengthen the resilience to censorship. Okay, so this was Aqua in a nutshell, and we'll look at all this in much more detail. However, if you go back, so we have, hang on, one more time. If we go back here and we have Aqua, so now we know that we have this location addressability of a service through Aqua in the network, through the node ID and the service ID. And now you ask, and then I told you that we have a request response model that actually forward chains responses without having to go back to the client at any given time, unless you literally need the result to update a browser page or whatever. It's nothing has to go back to the client. So the question now is, how do you do it? And there's one more foundation component you should know. We call it the particle. You can also think of it as smart packet. Basically, particles are conflict-free replication data structures. They combine the data and the execution sequence and a whole bunch of metadata. Let's ignore the metadata for the time being. Let's look at the data and execution sequence. The execution sequence literally is the compiled Aqua. That script, those 8 lines you saw, it gets compiled into what we call AIR, which is the Aqua Intermediate Representation, which is a low-level machine readable language output. It's not bytecode, but you can think of it as bytecode. It's at the same level of abstraction, at least. And what happens is you create, when you compile this Aqua script, you create, let's just say in the browser, a TypeScript client, which actually automatically is generated for you through the Aqua compiler. And then you create this particle. So if our name was ETH Global and our Boolean was true, then we create this particle with the data name and string, and we literally like fling it out on the network onto the first relay we can get to from the browser. Then at that relay, we have Aqua VM. it starts checking where's the service, which node, is it on this node, is it on a different node, and if it's on a different node, it forwards that particle to that node. The Aqua VM there now starts checking, okay, we got this greeting service here, we execute it, we get the high ETH global output, and then it checks where it's going, and in our case, it's going back to the client. And this is super, super powerful. It's basically a push smart data. It's a push data model instead of a pull data model. And it really, really adds a lot of a lot of attributes and capabilities that I'm not entirely going through today, but security in particular about data ingress, data or particle ingress and egress from a VM, from a processing perspective, plays a really big role in these smart packets. Okay, anybody have any questions at this point? I know I'm going fast, so if I need to sit down, tell me. Okay, hang on, let me look at the chat here. No. Okay. All right. No, that's cool. All right. No questions. So what we're going to do now is we're going to look at Fluence at IPFS. So I told you at the beginning that Fluence is a compute protocol, and basically it sort of to a certain extent requires developers to bring their own store. Within Fluence, we have adapters for file services on a node, SQLite, and a few other things. And one of the few other things is IPFS. IPFS itself being a Web3 optimized protocol, it's peer-to-peer, so it's a perfect complement to the Fluence compute. And what we've done is we basically build Fluence nodes with IPFS as a sidecar. That is, an IPFS node is deployed with on the Fluence node. And so let's switch here and let me go to the demo real quick. Let me show you what we're doing here. Okay. Come on. Okay. So let me overlap that with code as well. Otherwise, it doesn't make much sense. What we want to do is the following. We want to create a service that does something and then deploy that service to the Fluence network and then use that service. As a storage for that service, we want to use IPFS, not necessarily your local network. Yeah, your local storage. So let's start with the service. Where are we? Okay, so the service we want to build basically is a service we want to build basically calculates the size of a file. Okay, that's all there is to it. This is in Rust. It gets compiled to WebAssembly. It's pretty straightforward. It's only literally the simple part of Rust, not the complicated. There are no lifetimes. There are no generics, none of that, because in WebAssembly we pass everything by value. And with this little macro here, with this little keyword, we actually provide the compile instructions to use the appropriate types and the compilation into WASI32. So basically, the rest is just pretty standard. You read from the file and you calculate the file size. Very simple. So what we first would need to do is we are in the service directory here. And what we want to do is we want to build that Rust code into our compile target, which is WASI32. Now, of course, I've already done this. I think, yes, I have. And what we're doing is, I'll show you this in the build script. Basically, there's a bunch of noise in there, but what really matters is this. Marine, which is our compiler extension to Rust, basically builds this WebAssembly module. And then we just copy that module in a more favorable location, which we call artifacts. And here this is it. This is our file size compute WebAssembly module. And if we want to use it, we need to deploy it to a node on the Fluence network. And there's different ways of doing it, and one of them is to do it with IPFS. And I'm going to be very, very hang on. That's suboptimal. Hang on. I'm looking. Something disappeared. Okay. So I'm going to use the IPFS desktop. Now, I told you we don't want to just use any old node, IPFS node in this case. We want one that we control through, not control, but that's associated with a Fluence node. So what we're doing is we're in the web interface on how to Nice. Okay, this is not good. Dang it. It's just working. That's embarrassing. Let me try one more, but we're gonna get the same thing probably. Let me try language. Try it one more time. Okay, so this is no good.
So might be a node error. Node is not running.
Sorry, it's what? What was your?
I'm saying there is a node. The request it's sending is that node is not running. Maybe.
Okay. It should be running, but it's not.
IPFS node or maybe a Fluence node. Some of one of them.
All right. Okay, let me regroup here. Okay. Always fun when something works and then it doesn't. Of course, it never does it when you're not live. Okay. What we wanted to do was we wanted to take that service, put it on IPFS, and then deploy it with IPFS onto the Fluence network. And in order to do that, we use Aqua. Aqua, as I mentioned before, is the distributed language we have to handle those things. And this is what Aqua looks like. So basically, we have some services, and this is the deployment aspect of it. So basically, this little function here tells Fluence Compute to go to IPFS and add a module. It does this by creating a blueprint on the node. And hang on, Alexei is working on it. And hang on, we might be able to do this live after all. He was just there in chat. Oh, if I succeed at screen share, okay. All right, and we create the service for that module. So, okay, so now follow me mentally. It would have been much nicer graphically, but we created Rust code to calculate a file size. We compiled that Rust code into WebAssembly, WASI32. And for that, we have now a WebAssembly module. We take this module and we copy it onto an IPFS node, which I wanted to do with the desktop. In order to do that, we want to know the IPFS sidecar to use. That is, we need the multi-address of that node, which I wanted to get from the browser. And now we have that file sitting on IPFS, and you can deploy it, you can access it. As long as you have the CID, you can do just about anything you want. One way of us wanting to do is we wanted to do this with Aqua. And these are the functions we need to call in Aqua in order to take the module from IPFS and deploy it to a node of our preference. And it starts with deploy service. And we can just basically go through it. So the return of the deployed service is your service ID. And the service ID, as I said before, is the unique identifier for the service on a particular node, on a particular peer. So the location addressability comes from the peer ID, service ID tuple, which we briefly touched on before. So what we're doing now is we're going to find a relay. And now we want to get from IPFS with the CID and the multi-address. This is IPFS, is the multi-address, which we provided early on. And then we just go through building the service from the actual module. Because as I said before, you can build multiple services from the same modules. You can do different services from reconfiguring your modules. And basically the way it works is you basically take the module and then you just compute the hash of it. You then create what's called the blueprint from the hash, which basically entails all your dependencies, and you get a blueprint ID. And from that blueprint ID, we can now create the unique service ID. So everything up to service ID is totally reusable, and then the service ID is unique. Unless, of course, it doesn't work, then you get an error, which, by the way, okay, I see in chat. Okay, all right. Let me switch to Alexei to do the share. Let me stop right here. Alexei, are you ready?
Hello. That
Okay.
was a sudden. I was watching YouTube instead of Zoom, so I was a bit late. Sorry for that. Okay, let me close a few of wrong apps. Okay, so I'm sharing. I don't know why, but also the localhost stopped working, so I had to use this. It's a localhost, but in a different subnetwork. Anyway, hello everyone. I'm Alexei. I'm developer at Fluence, and I saw that it wasn't working for Bernhard, so I came here to help. So as Bernhard was describing, we have an IPFS demo that allows us to connect to some node in the Fluence network. So here we connected. It automatically retrieved the IPFS address from the Fluence node because each Fluence node is sidecarred with IPFS node, so they run together. and every Fluence node is connected to IPFS node through WebAssembly Fluence adapter, through WebAssembly IPFS adapter deployed on a Fluence node. And it knows address of IPFS node, so it reports here. And we can connect there through IPFS desktop. Let me restart it. I hope it won't connect automatically. So it asks us for IPFS node address. That's awesome. Let's connect there. So we have connected to the IPFS node running along the Fluence node. Now we have to click twice here. And now since what we want to do is to deploy WebAssembly service, we need to upload it to IPFS node. But okay, anyway, we have this IPFS node. You see here, it shows that it failed to upload. I wonder why. Never seen that before. But anyway, hope it will work. So what I did is I have this IPFS desktop connected to IPFS node, and it shows me that IPFS node has this WASM file. I know that it's a WASM file for a service written in Rust and compiled to WASM. So I copied CID, I pasted it here, and pressed deploy. And it deployed a new service by this CID, like IPFS file hash, a deployed service, and it's available to be called through this service ID. Awesome. So now when I copy this CID once again, what this service does, it allows me to calculate, to download a file from IPFS, another file, and calculate its size. So here, for example, I paste the same WebAssembly file CID, press get size, and it reports the size of this file, of this WASM file. Also, it uploaded this file size to IPFS node, and the uploaded file size, like a TXT file with this number inside, is uploaded to IPFS under this hash. So I paste it here. It should be a very, very small file. So yeah, it's just 6 bytes. Let's try another file. We have config toml here, just a random file. It's 116 bytes. I paste CID here, and we have this size. So it goes to IPFS through Aqua, downloads file to one of the Fluence nodes, applies a function in the WASM service to this file, calculates its size, and uploads the result back to IPFS. I'm done. Bernhard.
Okay, all right. Let me get back to screen sharing here. Take that back. All right. So, okay. While we're diddling around here, anybody have any questions? Really? All right. So we saw the code for I'm a little bit disjointed, so it's going to take me just a minute to get my train of thought back lined up here. So we saw the Rust code that turned into the WebAssembly module. We put the WebAssembly module on IPFS, basically permanent storage, distributed storage, permanent Web3 storage. So you can use it from anywhere, anytime, which is, in my opinion, at least in my case, a lot more reliable than saving something locally. And we've seen that we can deploy the service with Aqua in just a few steps. So the important part here is not just that you can do it with Aqua, but the important part is that you can interact seamlessly with the Fluence compute, with the Fluence node and IPFS. There is no separation. There are some backend services LXA implemented that allow you to do that, and that's really the, aside from it being cool that you can deploy this, blah blah blah. That's really the takeaway message, is that you can use Aqua seamlessly across different protocols. distributed compute protocols and store protocols. And that is really, really powerful. And then things like removing a service, obviously scaffolding is always more expensive than destroying things. It's always like build a house, then tear it down, and destroying is always fun. This is at the bottom, it's just you remove service in Aqua. This is how you remove a service in basically 3 lines. And again, it's the location addressability of the service that allows Aqua and the underlying network, Marine and Aqua VM, to take care of a lot of the headaches you would usually get. And one of the things it's important to know is that in peer-to-peer networks especially, peers come and go. It's not an exception. It's almost an expectation. It's in flux. It's a network in flux. And being able to work on this location addressability, and then there are ways of implementing failover, which are a little bit beyond the workshop. You'll see how truly powerful this is, especially compared to if you had to manually code that stuff. In addition, so and this was the actual file size calculator, which is very similar to what we had before. So the actual binding is the process file, blah, 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 which we had here. So these are the interfaces you use for that Rust service I showed you earlier. One was the size result, one was the write result, and then this is the actual service that provides you the bindings to the file size and the write file size functions. And one neat little thing is actually it's a very convenient, because I really, really dislike copy and paste or leave alone retyping. What we have is we have a REPL that allows you to interact with the WebAssembly modules locally. And oh, look, big surprise. Those are exactly the interfaces we were looking at before. So if I had a file path that with the string, then I could actually utilize that right here. And you would do something like this. And then put your file path in, and it would process. And that's how you can interact locally with the services. So if you want to test things out, or if you want to test your bindings, if you want to reconfigure services, this is a really cool way of doing it. And of course, through Marine, which was the compiler we saw before, we can, hang on, I need to know where I'm going. We can export those interfaces I think it was process, right? All process files. God, today nothing is going as fully planned. Okay, so you can export those interfaces, and if you wanted, you could just pipe them straight into whatever file you want to, and then you end up with a file like this. Okay, so this is sort of a quick start on how to set up your service, your module, your service deployment, and then your Aqua coding using the necessary bindings or interfaces from your services. And when we start looking in the actual components, the application logic now, if you integrate it with the browser code, is here. And one thing I wanted to show you is These are the actual Aqua files, the way you saw them before. We've seen this in VS Code. And if you compile it, all right, there's some dependencies, it doesn't work. If you compile it, you end up with, where are we?
In build folder, I think.
Alexei, do you know where the Aqua output, the compiled Aqua output files went? They used to be in here. God, where'd they go?
Well, maybe they're.
Okay, they're okay. They got moved to a different directory. Okay, so basically what happens is if you compile it, you can compile it in a way that it wraps your output Aqua code directly into a reusable TypeScript wrapper. So let's just have a look if we can find one that we used before. So get from, for example, that's what we looked at. So this is how you do the get from, and how the compiler prepares it for you, so you can just call that function straight from your client. And this stuff in here, this is actually air, and this is the machine level code. And believe me, it's not fun to write by hand, and but it's extremely powerful. And what the compiler does, it basically wraps that. And this is the part when we said the execution script is part of a particle, that is the execution script. This is part of the execution script. And this is what gets executed on the Aqua VM. And sorry for this ending up fairly disjointed. So if you have any questions on that, hit me up or hit us up in Discord. And now let me go back to the presentation, because I do want to go over the bounties. That should be fine. And if you have any questions, please shoot. Okay, prizes. So we got, actually, let me make that smaller. We got, no, that's not what we wanted. We got, God, there's like nothing working today. Nothing. I really, really apologize. Okay. We get multiple prizes. So we have a really, really simple bounty, $150 for the first 10 submissions. That basically extends our quick start. If you look in our examples, it's in Fluence.dev. In the examples, there's in the documentation, there's a quick start section. And we would like you to extend this and basically add a service, just like we showed you, that counts words of a message. That's it. And I think even in this disjointed presentation, you should have gotten everything you needed to do it. Now, you don't necessarily have to use IPFS to do the deployment. There are other command lines that are outlined in the quick start. But that's a real easy way to stick your toes in the water and play with some concepts, make a little bit of money, and see if you want to go on with the hackathon, which we really, really hope you want to. And the next bounty is $2,500, best use of Fluence Compute for your decentralized application. I give you a few examples here. So for example, NFT creation. With the marketplaces, the way they're going, it doesn't really matter anymore where NFTs get created. So one way of, and there are examples of people using Fluence already to create NFTs. And there are some pretty interesting ways of creating metadata around NFTs that also work with Fluence. For example, you can do mutable metadata for an immutable NFT using Ceramic, for example, or general, or if you just want to do an IPFS by yourself, that's fine as well. And so using something around NFT creation, maybe based on gas arbitrage across different EVMs, for example, that's something that'd be super interested. Price oracles, particularly price oracles that go straight to the DEX. Reusing already an aggregator, that's kind of lame. But if you go straight to the source and start pulling from DEXs, particularly if you start bringing liquidity information with it, that's also super interesting to us, and we would love to see that. And then another example would be, for example, to arbitrage contract use across different EVMs. Whether it's layer 1 or layer 2, if you have, say, a given contract that's deployed on multiple EVMs, obviously, when do you use which one? And it's actually not that different than how to do order routing to DEXs, right? So you can start checking on gas prices on the different EVMs and then start using the contract for whatever execution you wanted to use on those different EVMs. And then we have another price. It's $2,500 for best tooling or pattern for other developers to use. And things in there are really about porting existing libraries or library functions to Fluence, whether it be a Web3 library, for example, or just a signature signing verification service, where verification is interesting as a network solution. If you have domain knowledge in decentralized identities to verify credentials, we'd be interesting to see what you could do with that, in particular about linked data and resolving linked data. If you use BBS Plus, it would be really cool, because that is really where everybody's settling on right now in verifiable credentials. And we have one more, which is basically if you're into front-end development, Decentralized Network Explorer of our network. And there we have some examples that are listed on the bottom here. And then lastly, we have a $1,500 best use of Fluence with another event sponsor bounty, and basically just use Fluence, integrate it with one of the other event sponsors, and whoever comes up with the best use of it, $1,500 are yours. Going back here, just one more on resources. So there's a variety of resources. We have a Discord channel. We have a Discord channel in ETH Global. We have a Fluence YouTube channel. We are available in Discord, but if need be, you definitely can book some time with one of us, and we'll answer all your questions and help you sift through what needs to be sifted through. And lastly, if you're interested in peer-to-peer, we're hiring. Have a look at our website, and that's it. That's all I got. Sorry for the whatever that was.
No problems. Thank you so much, Bernhard, for this workshop, and thank you to Fluence for sponsoring ETHOnline this year. Just like what he said, I really want you guys to continue this conversation in the Fluence sponsored Discord channel. So yeah, you can find Bernhard there and ask him any questions if you guys have any that pop up while you're using Fluence during the duration of the hackathon. But yeah, everybody have a really great day, and I'll see you at the next workshop. Bye.